Good morning, everyone. This is our last chapter. Yeah, after this chapter, yeah, we will finish all the content about college physics too. Yeah, hope you have already learned something. Yeah, so many things I know, like in a short time. Yeah, just in 5 weeks, we learn so many things. Actually, I know like after maybe 1 month or 2 months, you will forget everything we talk about now. But what I want you to get is there is these things. Yeah, there are some like things existing like when you see some phenomenal, some applications in the real world, you will think about what we have already talked about that, and what is related to that. Yeah, that will be good. Yeah, we have already learned that. Yeah, and you can if you want to uh, delve into that, and you can do some research. Yeah, okay, today we will start the next chapter. After today's class and tomorrow's class, and we will finish all the classes. And if you have any questions, problems, just let me know. Okay, and let me share my screen. Okay, yeah, in this chapter, like chapter 25, yeah, we mainly focus on EM induction and EM waves. Does anyone know what is EM? Actually, it is short for electromagnetism. Yeah, you can see it includes two parts, electron and magnetism. Yeah, in physics, electromagnetism is an interaction that occurs between particles with electric charge via electromagnetic fields. Yeah, so like I said, when we talk about NASA chapter, yeah, this chapter actually it mainly focus on the interaction between the electric things and magnetic things. Yeah, so uh, we will talk in this chapter we mainly focus on EM induction and EM waves. Yeah, those are two different things. Yeah, they are related, but they are two different things. Okay, let's talk about what are those things and how can we use those things in our real life. Yeah, okay, let's begin. Yeah, this chapter's goal is to understand the nature of electromagnetic induction and electromagnetic waves. Yeah, you can see this EM. It is just a short name for electromagnetic. Yeah, and from this name, you will know it's something combine the electric things and the magnetic things. Yeah. Okay. Let's okay. Let's talk about today's goal. Yeah. For today's class goal, firstly, we will explore induced currents, and we mainly focus on the current currents interact with a magnetic field like that. And then we try to understand the motional EMF. Do you remember what is EMF? Are you familiar with EMF? Actually, we talk about this in chapter 22 when we talk about batteries and EMF. Actually, when we talk about the EMF last in chapter 22, it is like the maximum voltage for the batteries. Yeah, actually here is a similar thing. It is just the let me yeah, it's just the voltage induced in a conductor when it moves through a magnetic field. It actually it's just the relationship between the voltage and the magnetic field. So for this one, it's just a current with a magnetic field. For this one, it is just like a voltage with a magnetic field. Yeah, and then finally we will study like a magnetic flux and Lenz law, and we will talk about that and one by one. Okay, let's start this class. And before we start this class, let's do some preview. Yeah, and for in the chapter 25, firstly we will talk about the magnetism and electricity. Yeah, like I talked about in the beginning of this class, in in chapter 25, we mainly focus on like the interaction between the magnetism and electricity. Yeah, so yeah, the turning, you can see the turning windmill blades rotate a well core in a magnetic field, producing an electric current. Yeah, you will like continue to explore the deep connection between magnetism and electricity. Actually, in another chapter, chapter 24, like magnetism, magnetic fields and magnetic forces, you can see like the currents also can generate the magnetic fields, and also can generate the magnetic forces. Yeah, it has the relationship. Yeah, in this chapter we will explore the deep connection between magnetism and electricity, and then we will talk about induction. Yeah, a physician programs a pacemaker by using a rapidly changing magnetic field to induce a voltage in the implanted device. You can see here. Yeah, this one is just an application for induction. Yeah, and for this part, you will learn to analyze electromagnetic induction qualitatively and quantitatively. Yeah, from two different facts angles to learn and analyze electromagnetic induction. Yeah, and then we will learn like the electromagnetic waves. Yeah, you can see the vertical antennas. Yeah, this one on this cell phone tower emit electromagnetic waves. Yeah, waves of electric and magnetic fields. Yeah, now we will learn the properties of different magnetic waves from radio waves to light waves. Yeah, we will learn about that. Okay. Yeah, before we start this class, and let's looking back at the traveling waves. Yeah, actually the traveling waves we talk about it in chapter 50. Yeah, you learned the properties of traveling waves. Yeah, for sinusoidal waves, the wave speed is a product of the wave's frequency and wavelength. Yeah, just remember this equation. Yeah, the wave speed equal what wavelength multiple the frequency. Yeah, and in this chapter you will see how the properties of traveling waves are used to describe electromagnetic waves. Yeah, actually you can see the also we can use some properties of traveling waves to describe electromagnetic waves. Yeah, we will talk about that. Okay, and okay, let's stop to think this question. Yeah, to like review the traveling waves. Yeah, a microwave oven uses 2.5 gigahertz electromagnetic waves. A cell phone uses electromagnetic waves at a slightly lower 1.9 gigahertz frequency. What can you say about the wavelengths of the two? Actually, we talk about the this kind of like the magnetic waves. Actually, if the speed travel, it's around like 3 multiple 10 power 8. It's this one is like waves travel in vacuum, but it's around like around like approximately equal to like in the air. Yeah, so the speed is for this one is the same, and the equation is V equal what like lambda multiple F. And then this one has a higher, the microwave has a higher frequency, am I right? Which means it will has a lower wavelength. Yeah, does it make sense? Does it make sense to you? Not lower, shorter. Yeah, shorter wavelengths. Yeah, and this one, the phone should have like a longer wavelength. Yeah, does it make sense to you? So which means the answer should be. Does it make sense to you? Yeah. Yeah, you just use this equation, and the speed is the same thing. For two different for different electromagnetic waves, the speed is the same thing. Yeah, then you use this equation to decide which one is right. Yeah. Okay. Let's talk about the induced current. Induced currents, and you can also review this video. I will now play this video here to save the time. Okay, and we know, like for the induced currents, and we now know that a current can create a magnetic field. We have already talked about in chapter 24, yeah, in last class. Yeah, can a magnetic field current create a current? Yeah, do you think? Have you ever think about this question? Yeah, actually, Michael Faraday like experimented with two coils of wire wrapped around an iron ring in an attempt to generate a current from a magnetic field. You can see this is an iron ring, and when you closing the switch in the left circle, and then you will find that there will causes a momentary current in the right circle when you like closing the switch in this part. Yeah. So like the Faraday's experiment did not generate a steady current. However, in the instant he closed the switch in the circuit, there was a brief indication of a current. He realized that a current was generated only, the current was generated only if the magnetic field was changing as it passed through the coil. Yeah, if it is not changed, the magnetic is not changed, it's not changing, and there will not be a current. Faraday then set up a series of experiments to test this hypothesis. Yeah. And Faraday placed one coil directly above the other. You can see. Just there is one coil and there is another. There was no current in the lower circuit while the switch was in the closed position. Yeah, even this one in the closed position. Yeah, there is no no current. But a momentary like a current appeared whenever the switch was opened or closed, which means if the switch if the switch here is closed or open, and at that moment, yeah, there is a current in this circuit. Yeah, what does that mean? Which means only this one changed. Yeah, you can see if it open and close in that moment, there will be some, like, because it will no current or have current, which means there will be a magnetic field change, and then this one will have the current. Otherwise, there is no current. Okay, let's continue. Like Faraday pushed a bar magnet into a coil of wire. This action caused a momentary deflection of the needle in the current meter. Yeah, this one. Yeah, although holding the magnet inside the coil had no effect, which means if you just put the bar magnet here, this one there is no current. But if you push or pull the magnet, and there will be a current change, which means only the when the magnetic field changed, and there will be a current. A quick withdrawal of the magnet deflected the needle in the other direction. Yeah. Okay. Faraday created a momentary current by rapidly pulling a coil of wire out of a magnetic field. There was no current if the coil was stationary in the magnetic field. Pushing the coil into the magnet causes the needle to deflect in the opposite direction. Yeah, this experiment also tells us the magnetic field change makes created the current. That makes sense to you? Okay, Faraday found that there is a current in a coil of wire if and only if the magnetic field passing through the coil is changing. So the current in a circuit due to a changing magnetic field is called an induced current. Yeah, so this is what we talk about in this section, induced current, and then you know what is an induced current. The creation of an electric current by a changing magnetic field is an example of electromagnetic induction. Yeah. Okay, let us check some questions. A metal bar moves through a magnetic field. The induced charges on the bar are, yeah, you can see this one. This blue line is the magnetic field, am I right? And this bar, this metal bar moves through a magnetic field. The induced charges on the bar are which one? Actually, you can see from here to here to here, the magnetic field. Does it changed? Is it changed? Does it change? Yeah, actually, it's not. Everywhere is the same thing. So which means there is no current. Yeah, the induced charges. There is no induced charges. Yeah, does make sense to you? Because the magnetic field doesn't change. Does make sense to you? Yeah, so the answer should be E. Okay, let's talk about this one. A metal bar moves through a magnetic field. Yeah, the induced charge on the bar are. You can see this one, it is the direction is go out of the plane. Yeah, that makes sense to you. Yeah, if we learn this symbol in NASA class. Yeah, the dot means it the dot means it out of plane. That makes sense to you. Yeah, and then what is the situation for the induced charge? Yeah, actually, for this question, you can see, there will be a magnetic field change, and actually for this question we can use the right hand rule. Yeah, use your thumb pointed to the velocity, and also use your index finger go to point to the magnetic field direction. It will point it to you, and then you will find the force. The magnetic force will point to the left. Yeah, and then you will know. We talk about it in last class. If the for the positive charges, and it will go to the left. Yeah, and for the negative, it is opposite. The force is opposite, so it will go to the right. Yeah, so which means for in the original it will randomly setting, but after it goes through this magnetic field, then you use right hand, you will find the positive will have this force, and the positive charges and negative charges have this direction force, which means the positive charge will go to this direction and the negative charge will go to this direction. And then you will know we need to choose B. That makes sense to you. Okay, let me yeah, you can see this is the velocity's direction, am I right? Go down. And then this one just point to you. Yeah, you can see in this question. And the direction of a magnetic field is just point out to the plane. And then this one is the positive charges force direction. It go to the left. And then, which means the negative charges will go to the left. That makes sense to you? Okay. Let me continue to share my screen. Okay, so the right answer should be B. Okay, let's check this question. An induced current flows clockwise as the metal bar is pushed to the right. The magnetic field points. Yeah, actually, yeah, we can consider this one is a velocity direction. And this one is just like this is current direction, but also the positive, also the charges move direction, which means this is the force direction. Am I right? Like the magnetic force direction, because the magnetic force makes the charges move and generate the current. And then you know the velocity direction and you know the force direction, and then you can use the right hand rule to find the magnetic field direction. Let me show my figure to you. Just like this. Yeah, this is just the velocity direction, and this is the forces, magnetic force direction. And then you can see this is the magnetic field direction. It is into the screen. So then the answer should be C. Yeah, that makes sense to you. Okay, let me share my screen again. Yeah, so the answer should into the screen, like using the right hand rule. Actually, we can use the other way to decide the answer for those questions, but we will talk about it later. Okay, yeah, the answer is C. Okay, let's talk about the motional EMF. Yeah, the motional EMF is the voltage produced by the motion of a conductor in a magnetic field. Yeah, as a conductor moves through a uniform magnetic field, the charge carries inside the conductor also move with the same velocity. In a simple case where the velocity is perpendicular to the field, the charge carries experience a force. This one, yeah, we can use this one to calculate the force. And the positive charges are free to move and drift upward. Yeah, you can see from let's talk about this from this figure. Yeah, there is a conductor here, and the charge carries in the conductor is very experience a force of magnitude. This one, and the positive charges are free to move and drift afterward. Yeah, because you can see if this is velocity and this is this is magnetic field direction, and we can easily find the force direction using the right hand rule. Am I right? Yeah, you can use your right hand to find it. Yeah, and the positive charges are free to move and drift afterward. Okay, because of the electric forces. Not electric, sorry, magnetic forces. Okay. And the forces on the charge carries in a moving conductor cause a charge separation that creates an electric field in the conductor. The charge separation continues until the electric force balances the magnetic force. Yeah. Then we have this equation, like the force for the electric field and equal QE equal like the balance, the electrical force balance, and equal QVB. And you can see the resulting charge separation creates an electrical field. Yeah, because you can see if, like I said, in this conductor, the positive charges moves upward, and then the negative will like left in the downward. That makes sense to you. Then here is the negative, here is the positive, and then there will be a here is a positive, and here is the negative, and then there will be a or there will be an electric field in the conductor. Yeah, and this electric field increases as more charge flows. Does it make sense to you? Yeah, and you can calculate the force for the electric field, and equal this one, and equal the balance, and equal this one. Yeah, and when the electric force balances the magnetic force, the carriers experience no net force, and thus undergo no further motion. The electric field strength at an equilibrium is this one. This is equal VB, and here when these two force equal with each other, yeah, and there will be the electric field strength at equilibrium, and the magnetic force on the charge carries in a moving conductor creates an electric field, this one, inside the conductor. Yeah, and this is the velocity of the conductor, and this is like the magnetic field, magnetic, yeah, magnetic for the magnetic field. And then we can calculate the electric field strength. Yeah, magnitude. Yeah. Okay. Yeah, the motion of the wires through a magnetic field induces a potential difference, because you can see, yeah, this is just like it's just similar like there will be a potential difference, because this is the positive, this is negative. There must be a potential difference. That makes sense to you? Yeah. Induces a potential difference between the ends of the conductor, and this the potential difference is equal this one. Yeah, this is the like induces potential difference. Yeah, this is the velocity, and this is the I current, and this is the magnetic field. The potential difference depends on the strength of the magnetic field, this one, and the wire's speed, yeah, this one, through the field. Yeah, and then let's talk about, continue to talk about that. A battery uses a non-electric force to separate positive and negative charges. We know, like in the battery we use a chemical like force. Yeah, I don't know if you remember that. And a charge separation due to the conductor's motion is defined as a motional EMF. Yeah, if the charge separates due to a conductor's motion, and then we call it motional EMF. Yeah. This is yeah, you can see the chemical. It's similar with the chemical. This like a motional EMF is similar to the chemical reaction in the battery. Yeah, you can see the chemical reactions separate the charges and cause a potential difference between the ends. This is a chemical EMF. And the magnetic forces separate the charges and cause a potential difference between the ends. This is a motional EMF. Yeah, that makes sense to you. Okay. Oh, yeah, I just make a mistake. Yeah, this is L. This is the length of the conductor. Yeah. Okay. Yeah. So let's continue to talk about that. The motional EMF of a conductor of length, it is just L. Yeah, sorry. And moving with velocity, V perpendicular to a magnetic B is yeah, this one. This one is we just it's the same like equation here. Yeah, this one is the motional EMF. EMF due to a motion of conductor, and this is a speed of conductor perpendicular to the magnetic fields. And this is the length of the conductor, and this is the magnetic field strength. Yeah, that makes sense to you. Okay, let's talk about this example. Yeah, finding the motional EMF for an airplane. A Boeing 747 aircraft with a wingspan of 65 meter. Yeah, it's cruising at I just give you a tip when you try to resolve those kind of problems. Just like circle every important information. Yeah, it's cruising at 260 meter per second over northern Canada, where the magnetic field of the Earth. Yeah, this one is directed straight down. What is the potential difference between the tips of the wings? Actually, this one is it's now difficult. Yeah, we just talk about it is equal. Yeah, using this equation, it's equal V L B, and we know the V here, L here, B here, so we can calculate the motional EMF. Does it make sense to you? Yeah, like the potential difference. The wind is a conductor moving through a magnetic field, so there will be a motional EMF. We can visualize a top view of this situation, exactly as in figure 25.3b, with the wind as a moving conductor. Yeah, it's just similar like this one. Yeah, like this one. Okay, and the magnetic field is perpendicular to the velocity, so we can compute the potential difference using equation 25.3. Yeah, just this equation. And yeah, we know the like speed, and we know the length of the winds, and we know the magnetic field. Then we can calculate the potential difference. Yeah. You can see the Earth's magnetic field is small, so the motional EMF will be small as well. Yeah, unless the speed and the length are quite large, the tethered satellite generated a much higher voltage due to its much greater speed and the great length of the tether. Yeah, the moving conductor. That makes sense to you? Okay. Let's talk about the induced current in a circuit. Yeah, actually, the motional EMF is just like a induced like a voltage induced like a potential difference. Let's talk about the induced current in a circuit. Yeah, a moving conductor could have an EMF. Yeah, but it could not sustain a current because the charges had nowhere to go. You can see here. Yeah, the positive charge carries in the wire are pushed upward by the magnetic force. Yeah, here and the charge carries flow around the conductor loop as induced. Sorry, this one is the negative, and this is the conductor carries flow around the conducting loop as an induced current. Yeah, and if we include the moving conductor in a circuit, we can sustain a current. Yeah, actually, yeah, if you just put a conductor in a magnetic field, yeah, there is a EMF, motional EMF, but it cannot go to anywhere. But if we include the moving conductor in a circuit, yeah, we can sustain a current. The figure shows a length of a wire with resistance R sliding with speed V along a fixed U-shaped conducting rail. Yeah, you can see here. This wire has a resistance R. Yeah, and this is a conducting rail fixed in place, and this length of wire free to move. Yeah, and in the circuit, the charges that are pushed toward the ends of a moving conductor in a magnetic field can continue to flow around the circuit. You can see this one. Sorry. Yeah, this one is positive, and then it will like will form a current. like this. Does it make sense to you? Yeah. And the moving wire acts like a battery in a circuit. That makes sense to you. It's just like because it has a EMF. Yeah. And the current in the circuit is an induced current. Yeah. So we call this kind of circuit, it's an induced circuit. The induced current for a circuit including a wire with resistance R is given by Ohm's law. Yeah, because we know the EMF, motional EMF, and we know the resistance, and then we know the current. Yeah, and the potential difference equal this one. We just talk about that. This is L. Just pay attention to that. This is the magnetic field, and this is the spin of the conductor, and this is resistance of conductor. Okay. Now we can use Ohm's law to calculate the current. And in a circuit, a moving wire connected to rails in a magnetic field will carry an induced current I. The magnetic field will exert a force on the current in the direction opposite the wire's motion. You can see, exert a force on the current in the direction opposite the wire's motion. Yeah, this magnetic drag will cause the wire to slow down and stop unless we exert an equal and opposite force to keep the wire moving. You can see, yeah, this one actually it goes to this direction, but it will form a force to this direction, and this conductor will slow down, yeah, and stop unless we push it. For example, we push it with more like a force, yeah, and the force required to pull the wire with a constant speed v is this is pull force, and this is the magnetic field force. It equal this one, and this is the current. This is just the like a length of the conductor. Yeah, and this is the magnetic field. And then the current, we know that this one here is equal this one, am I right? So, which means it will equal, replace this one, will replace current with this one, and this is L. Yeah, this is also L. Yeah, just pay attention. Maybe I will modify it later. Yeah, and then you can see it will equal this one, V L squared B squared divide R. And this is the force required to pull the wire with constant speed. Okay. Yeah, here, this is a diagram to describe what we just talked about. Yeah. This is the induced current flows through the moving wire, and this is the magnetic force on the current carrying wire is opposite the motion. Yeah. And here there is a pulling force to the right must balance the magnetic force to keep the wire moving at a constant speed. That makes sense to you? Okay. Yeah, in chapter 10, yeah, you have already learned this, and you learned that the power exerted by a force pushing or pulling an object with velocity v, and is this one. Yeah, the power equal F multiple v. And the power provided to a circuit by a force pulling on the wire is the similar thing. The power input equal pull and the V, and we know like the F equal this one. Am I right? Equal this equation, and then we just put F P will equal V L, this L, L square B square R, and put it here, and multiple V, and then we can get this equation. Yeah, that makes sense to you. Yeah, and this is just L. Yeah, and the resistance in the circuit causes the power in the circuit to dissipate. Yeah, this is what we talk about in chapter 22, 23, like that. And this is the power equal I squared multiple R, and it's just the same thing. Yeah, because we know the I equal what? Yeah, VLB here. Yeah, it's here. VLB divide R divide R and then square and then multiple R and you will get this one. So the identical results make sense. The rate at which work is done exactly balanced by the rate at which energy is dissipated. Yeah, that makes sense to you. Okay. And because there is a current, power is dissipated in the resistance of the rail. Putting to the right takes work. This is the power into the system. Yeah. Okay. Let's talk about the generators. Yeah, this is the application for induced motional EMF and induced current. Yeah, a generator is a device that converts mechanical energy to electrical energy. Rather than move a straight wire through a magnetic field, it is more practical to rotate a coil of wire as the coil rotates. One edge always moves upward through the like electric field, while the other edge moves downward. Yeah, the motion of the wire induces a current, which is then removed by brushes that press up against rotating slip rings. Yeah, you can see this one. Yeah, as the coin or generator rotates, you can see so like as the coin or generator rotates, the sense of EMF changes. Yeah. When it rotates, the sense of the EMF changes, given a sinusoidal variation of EMF as a function of time. Yeah. So the alternating sine of the voltage produces an alternating current. So we call such electricity AC. Yeah, it's alternating current. Actually, we will not talk alternating current in this class. Yeah, but if you are interested, there will be another specific class called electronics. Yeah, you can have that class. Okay, yeah, you can try this by yourself. No work, no light. Yeah, turning the crank on the generator flashlight rotates a coil of wire in the magnetic field of a permanent magnet. With the switch off, there is no current and no drag force. It is easy to turn the crank. Closing the switch allows an induced current to flow through the coil. So the bound nuts, but the current in the wire experiences a drag force in the magnetic field, so you must do work to keep the crank turning. This is the source of the output power of the current, the line of the bump. Yeah, you can do this small experiment by yourself. Okay, let's talk about magnetic flux and Lenz law. Yeah, you can also view some video for Faraday's law and Lenz law. Yeah, I will now play this video here. Yeah, Faraday found that the current was induced when the amount of magnetic field passing through a coil or a loop changes. This is what happens when we slide a wire along a rail. The current expands and so more magnetic field passes through the larger loop. It's time to define more clearly what we mean by the amount of field passing through a loop. Yeah. Yeah, what the amount of field passing through a loop. Yeah, we can think about the amount of magnetic flux passing through a loop in the same way we think about the amount of air a fan blows through a loop. Yeah, the amount of air flowing through a loop depends on the angle. Yeah, you can see. Actually, if the angle is this one, yeah, and there will be more like air. But if this one, yeah, there will be less air through the loop. That makes sense to you? Yeah, tipping the loop changes the amount of air through the loop. We can look at a set view of air being blowing through a tipped loop. Tipping the loop reduces the amount of air that flows through the loop. Here you can see. Tipping the loop reduces the amount of air that flows through. Yeah. And if we consider the front end view of a fan blowing air through a loop, we can see that the tipping causes a reduction in airflow. You can see. If you tip in the loop, reduces size of opening seen by the flowing air. Yeah, does it make sense to you? Here, the dots represent the front of the arrows, indicating the direction of the airflow. Sorry, the internet is not good. Okay. Yeah, the magnetic field passing through a loop is also affected by the tipping of the loop. The axis of the loop is a line through the center of the loop that is perpendicular to the plane of the loop. The effective area of the loop is reduced when the loop is tipped. The effective area is defined as, this one, AB cosine theta. The AB is just like the loop's two different edge, and the cosine theta is just the tip angle. Yeah, the angle theta is the angle between the magnetic field and the axis of the loop. Yeah, here. Yeah, this one, if the loop is just like perpendicular to the magnetic field, which means the theta is 0. And if if tipping the like a loop, and there will be a angle. Yeah, this is this is the x of the loop, and this is just the magnetic field. So this angle is the the angle between the magnetic field and the axis of the loop. Yeah, if this theta increase, which means like this one will be decrease. Does it make sense to you? Yeah. And axis parallel to the field, theta equal 0, and which means you can see the more like magnetic field, all the airflow will go through. And if the axis tipped by theta, yeah, there is an angle, and there will be smaller, like fewer like magnetic field goes through. That makes sense to you? Yeah, the magnetic flux depends on the strength of the field and the effective area of the loop. Yeah, this is we use this symbol to represent the magnetic flux equal efficient area of the loop and the magnetic field. And we know the efficient area equals the area of the loop multiple cosine theta. Yeah. And the SI unit, the international unit of magnetic flux is Weber. Yeah, 1 Weber is 1 WB, is 1 Tesla, multiple square meter, because you can see this one, the unit is a square meter, yeah, and this one is a Tesla. Yeah, so this is, and we use Weber to represent it. Okay, and then the magnetic flux is, you can see, theta, yeah, is an angle between the magnetic field B and the x of the loop. Yeah, and the magnetic flux through the loop is this one. Yeah, this is just the diagram for the magnetic flux. Yeah. And let's talk about some quick check questions. Which loop has a larger magnetic flux through it? We know like a magnetic flux equal what? A, B, cosine theta. Yeah, but here the theta is just the same thing. I think it's just like a 0. So which means this one, sorry, I think it's A B cosine. Yeah, like this one, the field is twice as strong, which means this one will become twice, and the theta will be equal BA2B. That makes sense to you. And this one, the square is twice as wide, which means this is A, this is A. Suppose this is A, this is 2A, this is 2A, and then the A should be 4A. Am I right? For this one, it should be 4AB. So this one is 2AB, this is 4AB. So which one, like which one is the larger one? The loop B. That makes sense to you. Okay. Yeah. Yeah, because we need to use this equation. This is the AB because this the theta is 0. Okay, let's talk about this one. A loop knob where knob area A is tipped at an angle theta to uniform magnetic field B. The maximum flux occurs for an angle theta equals 0. What angle theta will give a flux that is half of this maximum value, which means the maximum is just like AB, yeah, because the theta is 0, and we want the theta equal half AB, yeah, which means the cosine theta should equal half. So when the cosine theta equal half, and the angle should be what? Yeah, this is a very easy like a triangle question. Yeah, cosine theta equal half, which means this angle should equal pi divided 3, and pi is 183. It should be C. That makes sense to you. So the answer should be C. Okay, let's talk about this one. The metal loop is being pulled through a uniform magnetic field. Is a magnetic flux through the loop changing? And you can see, and we know the magnetic flux equal what? AB cosine theta. Yeah, here the cosine theta is 0, but it's 1. The theta is 0. So the magnetic flux is called AB. A is the same thing, and B also is the same thing. So will it be changed? No? Yeah. So the answer is no. Does it make sense to you? Okay, let's talk about this one. The metal loop is rotating in a uniform magnetic field. Is a magnetic flux through the loop changing? Yeah, you can see the like a magnetic flux. Yeah, equal what? AB cosine theta. If the metal loop is rotating, which means the theta is changed. Am I right? So the magnetic flux will be changed. Does it make sense to you? Yeah, so yes. Okay, let's talk about this example, like finding the flux of the Earth's field through a vertical loop. Yeah, at a particular location, the Earth's magnetic field is this one tipped at an angle of 60 degree below horizontal. Yeah, which means this one like this, 90 degree, 16 degree. Yeah, 10 centimeter diameter circular loop where sits flat on a table. What is the magnetic flux through the loop? Yeah, actually the flux through the loop is given by equation 25.9. Yeah, this one A B cosine theta. Yeah, we will need the angle theta and the area A, and then the figure shows the loop and the field of the Earth. Yeah, this is the field of the Earth, and this is the loop. This is the like a loop, and yeah. So the field is tipped by 60 degree. Yeah. So the angle of the field with respect to the x, yeah, because this is the x of the loop, and this theta. Yeah, this we want to this angle. It is 30 degree. So the radius of the loop, and then the radius of the loop. Yeah, we know the diameter is like 10. So the radius is 5 centimeter. So the area of the loop equal this one. Yeah, it's easy to calculate. And then we can use the equation. the magnetic flux through the loop is then this one, and we know the theta is theta here is 30 degree, and we know the electric field and we know the area, then we can calculate the magnetic flux. Yeah, actually this one is a small loop and a small field, so a very small flux seems reasonable. Yeah, that makes sense to you. Okay, let's talk about Lenz law. We can summarize all of the discoveries as follows. Yeah, current is induced in a loop knob where when the magnetic flux through the loop changes. Yeah, motion is not required to induce a current. Yeah, how do we determine the direction of the current in the loop? Yeah, actually you can see. Actually, yeah, from all of the discoveries we talk about just now, and actually the current is induced in a loop where it's not like depend on the motion. Yeah, it's just when the magnetic flux through a loop changes. Yeah, magnetic flux is the most important point. If this magnetic flux changes, which means there will be induced current. Otherwise, there will mm, not induce current. Yeah, but how can we determine the direction of the current in the loop? Yeah, we will talk about that. Yeah, the German physicist Henry like Lenz developed a rule for determining the direction of an induced current. Now we call it Lenz law. Yeah, Lenz law, there is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. The direction of the induced current is such that the induced magnetic field opposites the change in the flux. Yeah, let's explain this one. And you can see Lenz's law tells us to look for situations where the flux is changing. Yeah, the magnetic flux can change in three ways. Yeah, because it equal this A B cosine theta. Yeah, the first one is the magnetic field through the loop changes. Yeah, if the electric field like changes, and the loop changes in area or angle. Yes, this is area, this is angle. And the third one is the loop moves into or out of the magnetic field. If it is moved into or out of the magnetic field. Actually, I think this one is just similar with the first one. Yeah, the induced current generates its own magnetic field. It is this induced field that opposite this is the flux change. Yeah, you also can view this video for Faraday's law. This is related to this one. Yeah, but I think you have already learned this. Yeah, I'm now playing the video for here. You can see here. Yeah, there is a loop. Here is a loop, and here is a bar magnet. The magnet at rest creates a flux downward through the coil. Yeah, actually there is no change in flux because there is no change in flux, so there is no current in this one. Yeah, but moving the magnet downward increases the downward flux through the coil. Yeah, the loop needs to generate an upward pointing field to opposite the change. Yeah, a counterclockwise current is needed to induce the upward pointing magnetic field. Yeah, you can see. Yeah, since this is like a magnetic field generated by this bar magnets, and the loop, yeah, when it go downward, it will increases the downward flux through the coil. The loop needs to generate a upward pointing field to offset the change, and then there will be a current generate, and you can use the the right-hand law to, because you know this direction. the magnetic field direction, and then you can use the right-hand law to decide the current direction. You can see if you use the right-hand law, and you will know the current direction should go to this direction. It is a counterclockwise. That makes sense to you. Yeah, you can see. Let me show you my screen. Yeah, you can see it's just for the left side, and you can use this one, and then the current will go this direction. And for the right side, and you can use this right hand, and then the current will go this side, and so it is counterclockwise. Does that make sense to you? Okay, let me. Okay, and if the magnet is moving upward, if it goes to upward, I'm sorry, goes to upward, and the downward fluxing is decreasing, which means the downward point field is needed to opposite the change. There should be a downward point field. Yes, and then you can use the right hand rule. Also can find the direction, and it's just opposite. So opposite with this one. So the if you use the right hand, you can see the current is in this direction. Yeah, a downward point field is induced by a clockwise current. That makes sense to you. Okay, let's talk about how to use Lenz law. And this you can find this one in tactics box 25.1. Yeah, it is in page. It is in page 888. Yeah. Okay, let's talk about how to use Lenz law. Yeah, firstly, determine the direction of the applied magnetic field. The field must pass through the loop. Yeah, and then determine how the flux is changing. Is it increasing, decreasing, or staying the same? If the flux is steady, there is no induced magnetic field. If the flux is changing, determine the direction of an induced magnetic field that will oppose the change. Increasing flux, the induced magnetic field points opposite to the applied magnetic field. If there is a decrease in flux, the induced magnetic field points in the same direction as the applied magnetic field. And finally, determine the direction of the induced current. Use the right-hand rule to determine the current direction in the loop that generates the induced magnetic field you found in step 3. Yeah, that makes sense to you. Okay, let's talk about some quick check questions. Yeah. The bar magnet is pushing toward the center of a wire loop, which is true. Yeah, let's talk about this one. Yeah, actually, yeah, for this question, the right answer is clockwise induced current in the loop. You can see if you just up like this bar magnet go up, and the upward flux from magnet is increasing. So to offset the increase, the field of the induced current points down. Yeah, and then you can use the right hand rule, and this and the direction should goes to this. If it is goes down, and then it will to this direction. Sorry. Yeah, to this direction. And you can see. Let me show you. Yeah, you can see. It's just a go. Yeah, it goes down. So it should be this direction. Doesn't make sense to you. It is clockwise. Let me show my screen again. Okay, so the answer should be A. Okay, let's check this one. The bar magnet is pushed towards the center of a wire loop, which is true. Yeah, actually for this one, yeah, you can see the magnetic flux is 0. Yeah, so there is no change of flux. Yeah. So the answer should be there is no induced current in the loop. Okay, let's talk about this one. A bar magnet sits inside a corner wire that is connected to a meter for each of the following circle stations. Yeah, the first one, the bar magnet is at rest in the core, and the second, the bar magnet is pulled out of the core, and the third, the bar magnet is completely out of the core and at rest, and the fourth is magnetic. The bar magnetic is reinserted into the core. And what can we say about the current in the meter? Yeah, it is the current goes from the right to left, from left to right, and there is no current in the meter. Okay, let's check. Let's further check the first one. The bar magnet is at rest in the core, which means there is no like a magnetic flux. Does it make sense to you? So for this situation, the answer should be C. Yeah, because there is no like a magnetic flux change. And for this one, the bar magnet is pulled out of the coil, which means we need do opposite. So which means there will be this direction magnetic field. And then using the right hand rule, and you will know the current direction should go to this one. It is should from right to the left. That makes sense to you. To this is A. And the third one, the bar magnet is completely out of the coil and at rest. Actually, if it is out and at rest, which means there is no magnetic flux. That makes sense to you. So this one is also C. And this one, the bar magnet is reinserted into the coil, which means there will be an opposite magnetic field. It should be this one. And using right hand, it should be the current should goes up, and it should from left to right. Does it make sense to you? This is B. Yeah, obvious, because this one is A. Okay. Yeah. That makes sense to you? Okay. Okay. Let's check this question. Yeah. A magnetic field goes through a looped wire as at right. Yeah, this one. And if the magnitude of the magnetic field is increasing, decreasing, constant, what can we say about the current in the loop? Answer for each of the stated conditions. Yeah, actually, this one is very similar with the last one, but using different view. And you can see if the magnetic field is increasing, which means it should generate opposite magnetic field. This is the original is go into the plane, and the new one is should go out of the plan. Does that make sense to you? And then you use the right hand rule. Yeah, and you can see the current direction should this way. That makes sense to you? Yeah, so it is counterclockwise current. So it is B. That makes sense to you? And it is decreasing. Actually, it's just the opposite. Decreasing, which means it should be have the same direction electric field, and then use the right hand rule, and you will find it is this direction. It is clockwise current. It is A, and if it is constant, which means there is no magnetic flux change. So there is the loop has no current. Yes, C. That makes sense to you? Okay. Let's talk about this. Oh yeah, this is the answer for this question. Let's talk about this one. The magnetic field is confined to the region inside the dashed line. It is zero outside. The metal loop is being pulled out of the magnetic field, which is true. If there is a clockwise induced current in the loop, there is a counterclockwise, and there is no, because which means it is pulled out, which means the magnetic flux decrease. Am I right? That makes sense to you? and which means it should have the same like a magnetic field. Am I right? Then use the right hand. Then it should be going to the plane, and then use the right hand law, and the direction should go through this direction. Am I right? So which means the answer should be which one? It should clockwise. Does it make sense to you? Yeah. Okay. Yeah, this is the answer. Yeah, there is a clockwise induced current in the loop. Actually, this is the steps for this question. The flux through the loop is into the screen and decreasing. So to opposite the decrease, the field of the induced current must point into the screen. From the right-hand row, inward field needs a like a clockwise current. Yeah, that makes sense to you. Okay. Let's talk about this example. Yeah, and applying Lenz law. Like okay, I could, this one is just the wrong one. Oh, that's fine. Let us ignore that. A loop is moved toward a current carrying wire as shown in the figure. As the wire is moving, is there a clockwise current around the loop? Counterclockwise current or no current? Yeah, actually for this one, you can see the figure shows that the magnetic field above the wheel points into the page if you use a right hand, like a right hand rule. You know like the magnetic field in this area, it will point into the page. And we learned in chapter 24 that the magnetic field of a straight current carrying wire is proportional to like 1 divided r, where r is the distance away from the wire. So the field is stronger closer to the wire. Yeah, that makes sense too. So if the loop is moving into the region of the stronger field, the flux is into the page and increasing. Yeah, so the induced current must create a magnetic field out of the page to opposite it, which means create this one. Yeah, and so the right hand rule tells us that the induced current is counterclockwise. Does it make sense to you? Yeah. Okay. Yeah, as the loop moves towards the wheel, the flux through the loop increases. To opposite the change in flux, the increase into the page. The magnetic field of the induced current must point out the page. Thus, according to the right-hand rule, a counterclockwise current is induced, as shown in figure 25.70, this one. The loop moves into a region of stronger field, opposite the increasing flux. The induced field should be opposite the exiting field. So our answer makes sense. Yeah, that makes sense to you? Okay, let's talk about this one. A long conductor carrying a current runs next to a loop of wire. The current in the wire varies as shown in the graph. Which segment of the graph corresponding to the largest induced current in the loop? Yeah, which one? Actually, which means the largest induced current, which means the largest change about the like flux magnetic magnetic flux. Yeah, does it make sense to you? Yeah, so which like which means yeah here. Actually, for this question, yeah, we will use Faraday's law, and the Faraday's law tell us when the like a current like make have the biggest change, and this means like it has the largest induced current. It should be E. Yeah, actually, we will talk about Faraday's law in next class, like tomorrow's class. So yeah, and after that you will know this a lot more clearly. Okay. Yeah, the answer is E because this change a lot, which means there is a largest induced current. Okay, let's talk about this one. A battery, a loop number where, and a switch make a circle as shown. A second loop number where sits directly below. At the following times, like just before the switch is closed, immediately after the switch is closed, and long after the switch is closed, immediately after the switch is reopened. What can we say about the current in the lower loop? Answer for each of the state conditions. The loop has a clockwise current, the loop has a counterwise current, and the loop has no current. Yeah, actually this one is just similar with the before one. Yeah, if before the switch is closed, actually there is no current everywhere. So which means the loop has no current. That makes sense to you. Yeah. Immediately after the switch is closed, which means this is a positive and the current will go this direction and there will be a magnetic field. Yeah, use like the right hand rule, and you will find it should go upward. Am I right? And then there will be like an increase. Yeah, so which means it should be downward, generally downward. So which means there will be a opposite like a current. So it should be which one? Like a clockwise. Does it make sense to you? Yeah, so it should be A. Does it make sense to you? Long after the switch is closed, which means there is no magnetic flux change. So it should be C because the loop has no current. And immediately after the switch is reopened, yeah, which means this one, yeah, there is a current, but this one will smaller, which means it should generate up the same direction, this one. So it should be a counter clockwise current. It should be B. Does it make sense to you? Okay, yeah, this is the answer. Okay, let's talk about this one. Immediately after the switch is closed, the lower loop exerts like which a torque, an upward force, a downward force, or no force, or torque. Yeah, for this one, actually it is upward force because you can see the battery drives a counterclockwise current. Yeah, that briefly increases rapidly. Yeah, the flux through the top loop is upward and increasing. And to opposite the increasing, the field of the induced current must point downward. Yeah, yeah. And from the right hand rule, a downward field needs like a clockwise current, yeah, like this one. Yeah, the counterclockwise current in the lower loop makes the upper face a north pole. Yeah, and the clockwise induced current in the upper loop makes the lower face north pole here. Yeah. So facing north poles exert repulsive forces on each other. Yeah, does it make sense to you? So which means there is upward force. Does it make sense to you? Okay. Yeah, this is what we talk about in today's class. Yeah, we mainly focus on the induced voltage, like a motional EMF, and induce current, and how to like get the direction, how to calculate the when will be when there will be a induced current, only if the magnetic flux is changed. Yeah, and then there will be a induced current. And we also talk about how to calculate the magnetic flux and how to decide what's the direction of the current. Yeah, this is what we talk about in this class. And next class, we will continue to talk about those kind of things. And we will talk about the Faraday's law and the EM, more things about EM inductor and EM waves. Yeah. Okay. See you tomorrow. Bye.